Can you hear me? I can't hear you. I mean, very faintly.
Oh, there it is. Can you hear me now?
Yeah.
Right. Let me. No. So do you have slide control now?
I do, yes.
Cool. You sound not great.
I sound not great.
You sound like you're, I don't know, in a cave. You sound hoarse.
What about now?
That's better.
Okay. Testing, testing, 1, 2, 3.
Yeah, that's okay. We're gonna give it a minute. We've got, I think we had people. There's still snacks and whatnot outside, so. And I'm gonna hold out for a note taker. It seems to be okay. That's how you get rid of it. Who doesn't like it? He likes the lead. Everybody what? Stick his doesn't know what's going on. Okay, I think we're going to go ahead and get started. I do still need, so I am standing in, I'm your responsible AD. I'm standing in for the chairs because neither one of them could be here today. And so I'm running the show. But we need note takers before we can start. Too much, is that still the case? Am I still too loud? Good.
Hey, Thibaut here. I'm happy to take notes.
Awesome. So the note tool is set up, it looks like. So you should just be able to, we want actions and things like that. We don't need verbatim, obviously. Okay. So here we go. So this is KEYTRANS. And this is the note well. So if you are unfamiliar with this or you have not seen this before, then you need to read it and make sure you understand it, because you've agreed to abide by it by being at an IETF meeting. So normally there's what we call a note really well, which says that you agree to be respectful and polite and courteous. Maybe we've rolled that all into one thing. Anyway, so remote participants, you need to make sure that your audio and video are off unless you're presenting, and a headset is strongly recommended. For those in the room, wait, let me see. I don't think we have that. I think it's just the agenda. For those in the room, if you want to come to the mic, you need to be logged into Meet Echo so that we have a recording of you being here. And then if you want to come to the mic, then you can raise your hand and we'll call you up. Okay. So this is the agenda. Are there any agenda bashes? Oh, okay. All right. So I think we're on to Brendan. Let me pull the slides up. All right, Brendan. I'm going to pass you control.
Cool, thank you.
You should have it.
Okay, so let's get started. So this presentation is going to be going through all of the changes that have happened to the protocol document since we adopted it at about the last IETF meeting. And since the last IETF, there have been actually quite a lot of changes. All of the ones that have actually landed and been merged all center around this theme of authenticating time, which might seem kind of weird because the first draft actually had no concept of time and never mentioned it once. And that is actually consistent with the Merkle squared paper that we cite in the draft as sort of like the basis for this construction, because that paper never mentioned time either. And the thought was, surely that's okay. Like if we give people key transparency, that kind of is already this really powerful system for making sure that everybody agrees on some kind of arbitrary mapping between labels and values. And essentially what you want is a mapping between tree sizes and roughly the timestamp that they were published. And so intuitively, it kind of makes sense or like seems reasonable that you would be able to parlay KT in a pretty simple way into also a guarantee of what time it is. But that's not true, and we're going to talk about why. So specifically, the idea that we had about how to authenticate time originally was something called a clock label. And what this would be is just some label in a transparency log with a key that everybody knows or a label that everybody knows. And you would look up that label and the value of the label would be the current time. And you would expect this label to kind of be updated regularly. And then users can always look it up and they can see, oh, this is the current time. And if that time is roughly close to what their clock says, then that would be a signal that this portion of the tree was probably created recently. So in this graph that we have here, the x-axis is tree sizes as the tree grows over time. And then the y-axis is the value of whatever this clock label would be. And so generally, how we'd expect this sort of system to work would be that if the tree size has 20 entries in it, which is sort of the first third of the graph, then whenever we look up the clock label at about 20, and we see the timestamp that it maps to is about 20 seconds or whatever. And users will see that, they'll remember when the tree size was 20, I looked up the clock label, it had this version, and its timestamp was about 20. And if the transparency log ever in the future tries to show me a tree size with 25 entries, which is right in the middle, then I'll see that. I will look at the clock label and I will see, oh, this timestamp is less than it was before. That doesn't make sense if the tree size is greater. So something is wrong here and there's some kind of issue. The obvious kind of counterpoint to that is we can avoid that issue by just not letting the transparency log show you ranges of tree size where you will detect that the clock label is wrong, right? Because if you're going to reject it, I just won't show that size of the tree to you. If we only show Alice the tree sizes that are shaded in red here, and she only looks at the tree sizes that are shaded in red, she actually kind of gets the impression that the clock key is monotonic, how you'd expect it to be, even though it's not actually. Because you just see this first section, which goes up to 10, and then we go over to like 25 or so, where it goes up from 10 all the way up to the rest, and that kind of looks fine to her. And you can also kind of argue that maybe this is okay to have it work this way, where like, maybe bad things are happening in the middle, but if I don't look at the middle, maybe it can't hurt me, and so it's not an issue. And then the trouble kind of starts to appear when you consider that the transparency log can do the exact same thing, but with different subsections of the tree for different people. So if the log only shows Bob the tree heads that are in this blue shaded region, then he also thinks that the clock key is, or that the clock label is monotonic because he sees it go up to like 25, and then he sees it go up to like 25 to the rest, and he doesn't see this middle bit where it jumps around. And so he thinks it's fine, even though he's looking at a different subsection of the log. And of course, Bob can also maybe tell himself that this unshaded region is fine if it jumps around because he's not looking at it. But if you put these two kind of things together, this is kind of obviously a fork where whatever is happening in the blue region is only visible to Bob, and Alice never knows to look in there for anything. And in the red region, that's where only Alice can see, and Alice doesn't know to look in the blue region for anything. So like in the blue region, we can do all kinds of crazy things with Alice's label, and Alice won't know to look in there to see that her label's changed in ways they shouldn't have. And so, yeah, it's basically exactly the same security issue as a fork, which is why kind of surprisingly, the fact that there's a fork is not actually the security issue here. Forks are not okay, but if we wanted to put Alice and Bob on separate forks of the log, we could do that much easier. Like we could just sign different versions of the log and show one to Alice and one to Bob, and then they'd be on different forks. And the mechanism the document gives for detecting when a fork has happened is out-of-band communication. And so if Alice and Bob are on different forks, genuinely, then they can do out-of-band communication, and they can detect that they're on different forks, and then they have proof of misbehavior. And actually the same applies here, where if Bob is somewhere in the blue region and Alice is somewhere in the red region, if they have out-of-band communication at any point, then they will detect the misbehavior, where Alice will see like, oh, I'm in a part of the tree that's ahead of yours, but maybe I have a timestamp that's behind what you see, or something like that. And they'll be able to detect that something is happening that's not supposed to be happening. So the fact that there's a fork is not the issue. The issue is that out-of-band communication is not always available. And so even though Alice and Bob both kind of disagree on what's happening in the middle of the graph here, they both will happily accept the portion of the tree that's kind of in this in the third portion of the graph, so like past 35 entries. Yeah, and so even though Alice and Bob disagree on what's happening in the middle, they both are willing to accept the right third of the graph as like a valid extension of the tree. And so what the transparency log can do is once it's done doing whatever it wants to do on the fork, it can show both Alice and Bob a tree size with size 40. And so that would pull both of them into the right third of the log. And then once that happens, they're actually no longer on a fork. If Alice and Bob do out-of-band communication at this point, if they even talk to each other at this point, they'll say, okay, we agree on the tree size, we both agree it's 40, we agree on the root hash of the log, we agree on the timestamp. So if we do out-of-band communication at this point, we actually can't detect any evidence of misbehavior. And that's actually a really big deal because forks, when they happen to the log, are really supposed to be permanent. Because if a fork happens, we want to be able to detect that the server misbehaved, regardless of how long it takes us to detect it. And so it really shouldn't ever be possible for the transparency log to misbehave in this kind of way where it creates a fork and then to cover it up so that nobody ever knows. That's why this is an issue. So the actual solution that we worked out to this to kind of fix it was to make timestamps a more first-class feature of the protocol document. So before, log tree leaves were just prefix tree hashes. And so now they are a pair. It's a prefix tree hash with the timestamp of when the log entry was created. And then we require users that whenever they look at any log entry, they have to check that the timestamp of that log entry is consistent with the timestamps of all of the other log entries they've ever seen. And saying, we're going to check consistency with everything we've ever seen sounds kind of dramatic, but it's actually a lot less hard than it sounds because if you've read the protocol draft, you know that we define this idea of an implicit binary search tree, which is not something that's actually encoded or like shows up in the wire format anywhere. It's more so just a pattern for inspecting the leaves of the log tree. So in this picture, if I want to look at, say, like node 3, and I follow the implicit binary search tree, then I would have to start at the root node, which is 4 here, and then I'd have to go to 2, and then I'd have to go to 3. And because I start at 4, when I get to 2, I can check that the timestamp of 2 is less than 4 because it's to its left. And then when I get to 3, I can check that the timestamp of 3 is greater than 2 because it's to its right, but also less than 4. And so if users always kind of follow this implicit binary search tree structure, then any timestamps they accept are essentially always guaranteed to be actually monotonic, and you don't have this issue from the last slide where there are disagreements at different points of time at when certain subtrees of the tree were created. And then you can actually kind of, well, what you have to do to fix the vulnerability is pull that same logic to whenever you update from a previous view of the log to a new view of the log. And so really what that means is whenever a user needs to move to a newer version of the tree, the user needs to check that none of the timestamps of previous log entries were kind of covered up by the new tree. And so if you look here, if our initial view of the tree had 3 log entries in it, so the rightmost log entry was 3 here, and then we want to move to a view of the tree with 5 log entries, we want to check that the timestamp of 4 is greater than 3 because 4 is essentially a parent of this new subtree. 4 is a parent of the old tree that we saw. And then when you go from 5, from when the log has 5 entries to when it has 7 entries, you do the exact same thing, which is you look at the rightmost log entry, which is 5, and since it now has a new parent, which is 6, you want to make sure that parent doesn't cover it up, and so you make sure that the timestamp of 6 is greater than the timestamp of 5. And yeah, that's all that you really need to kind of fix the vulnerability that we talked about. You have to make sure that whenever users look at a log entry, they check this timestamp associated with the log entry is consistent with everything else. And also whenever users move to new versions of the tree, they sort of pull that logic over and make sure that none of the timestamps they saw previously are now covered up. But this sort of idea of putting timestamps with log entries actually introduces a lot of cool new features that we can do as well. So if log entries have timestamps now, then what that means is that essentially everyone can agree on how old a log entry is, which leads into this concept of maximum lifetime. So the maximum lifetime is a duration that a transparency log can define, and it's the duration of time after which log entries essentially die and they can't be used anymore. So if a user is like searching for something in a log and they're navigating the tree and they come across some log entry that they can see is expired, then they can see that it's expired and that is going to that's going to affect the outcome of their search. Right now, the way it's specified is that users get one freebie. So if a user is navigating the tree and they hit some log entry that's expired, I can actually look into that log entry and see how my search would progress from there. And if my search would progress to the left of that log entry, that's further into the expired portion of the tree. So I would just have to terminate my search with an error because those log entries don't exist anymore. But if my search would progress to the right, then I can actually continue because that's away from the expired portion of the tree. And so, yeah, and that's actually really cool because it allows provable and secure pruning of the tree, which is something that was required in the architecture document that we would have to support. But before we had this feature, I actually had no clue how we were going to support it. So that's good. And then feature number 2 that kind of comes out of this is something called a reasonable monitoring window. But to explain that, I kind of first need to talk about why specifically in contact monitoring mode, the protocol is secure. So if you kind of look at a timeline of requests, what happens first is that Bob looks up some label, which is owned by Alice. After Bob looks it up, Alice monitors that her label is correctly represented in the log. And then after Alice monitors her label, Bob checks that the version of the label he observed is still present. And so it's the fact that those requests are interleaved that makes the protocol secure, because if some malicious version of the label was added before Bob looked it up, then Bob would get that version of the label. And if that malicious version stayed in the log, then when Alice monitors her label, she would see it and that check would fail. But it could also happen that after Bob looks up that label, it later gets concealed by the transparency log, so you can't see it anymore. So then Alice's check for correctness would succeed, but then Bob's check that what he observed previously is still present would fail. So yeah, it's the interleave of these 3 requests happening one after the other that is how contact monitoring derives its security. So with that background, there's kind of a thought process we can go through here, which is that if log entries have timestamps now, then when I look up a label, I can see how long ago it was inserted. Okay, I just heard a weird sound, but whatever. When I look up a label, I can see how long ago it was inserted, and that kind of conveys something about how trustworthy the value is, because if it was inserted a long time ago, that seems like it would be more trustworthy than if it was inserted like 3 milliseconds ago. Yogesh?
Yeah, I have a question regarding the submission, because sometimes the transparency logs submit the request in a batch. So is this timestamp, how would that batch submission manifest with this thing which you are talking about? How does it work? Because would they all have the same timestamp for the things in the batch?
Well, so when you do a batch insertion of data into a transparency log, you only add one new log entry that's for the whole batch. And so the timestamp of that log entry would just be the timestamp of when the whole batch was published.
Yeah, but there are n number of entries in that batch, right? So will those n entries will have the same timestamp?
Well, the whole batch all goes into one log entry. So you can make multiple changes all in the same log entry, and then that log entry has one timestamp.
Okay. Thanks.
Yeah. But yeah, so the sort of concept of if a label was inserted a long time ago, doesn't that kind of tell me maybe it's more trustworthy or not? And so we have this concept of the reasonable monitoring window, which is defined as the duration of how long or how frequently the transparency log generally expects users to monitor labels that they own. And then the way we actually kind of operationalize that is with a third thing called distinguished log entries. So distinguished log entries are just log entries which are chosen according to a specific algorithm that satisfies the following criteria. The first one is that these log entries are regularly spaced. So we can expect there to be roughly one created per every interval of the reasonable monitoring window. Number two is that it's stable. So once we decide that some log entry is distinguished, it's always going to be distinguished. It's not going to stop being distinguished at some point. And then criteria three is that it's verifiable. So everybody can look at a log entry and agree if it's distinguished or not. And it's not like encoded into the log entry or anything. It's just decided based on its timestamp, whether it's distinguished or not. So then you can kind of think about the timeline going something like this, which is step one, Alice inserts some label. Step two, some amount of time passes, after which a distinguished log entry is chosen. That's to the right of where the label was inserted. And then Alice checks that her label is still correctly represented in that distinguished log entry specifically. So then what could happen sometime in the future is that whenever Bob looks up the label, that search for the label goes back to the first log entry where the label was ever inserted. And then he can also find that same distinguished log entry, which is the first distinguished log entry that's to the right of where the label was inserted. And if it already exists, which it usually will, then he can just check right away that in the same query that the version of the label that he observed is still present in that distinguished log entry. So these two checks, we can kind of coordinate them to happen at the same distinguished log entry. And if that already exists, then the user Bob that looked up a label actually doesn't have to maintain any state after the query. No, my headphones are dying. 1 second.
Oh, we lost him. Is he back? There he is.
This audio is still okay?
Yep.
Thank you. Okay, so the timeline is that Alice inserts some label. She waits for the next distinguished log entry to be created. She checks that her label is correctly represented in that distinguished log entry. And then whenever Bob looks up some label, he finds the first log entry where it was inserted, where Alice inserted it. And then he finds that same next distinguished log entry, and then he checks that he does essentially the same check, which is he makes sure that that version of the label that he found back in that earlier log entry is still present in the distinguished log entry. And what's nice is that these two timelines are kind of independent. So both Alice and Bob have to do the same thing, but they can do it essentially at any time. So when Alice first inserts the label, she actually has to wait for the next distinguished log entry to be created. So she has to like go away and come back. Bob might look up a label and see it when it was first created, in which case he would also have to go away and come back. But also if the label has been in the log for a while, he doesn't have to do that. He can just check right away that it's correctly represented. Yeah, and so sort of like I said before, Bob needed to wait a very long time to guarantee that between when he looks up a label and when he checks that it's still present in the log, there was time in the middle for Alice to do her requests, because we needed these requests to be interleaved in time. And what that incentivized was people to have really long retention times where Bob would look up a label and then he would have to hold on to it for like 6 months or something, just on the off chance that Alice is offline for a really long time. Now, in this kind of new model where these checks are coordinated to happen at the same distinguished log entry rather than be interleaved in time, these checks can essentially happen at any point in time. So now if Alice is offline for a very long time and there are a lot of new distinguished log entries that are created while she's offline, she can actually kind of catch up and just go to these old distinguished log entries that she missed and check each of them serially. And that takes more effort, but it also means that users that look up a label don't have to retain it for the longest possible time that Alice might be offline, which essentially means that how long users that look up a label have to retain it is more of a function of efficiency in terms of making monitoring easy for people that own labels, so they don't have to check every hour a new distinguished log entry or whatever. It's more about efficiency for label owners rather than making sure this window is long enough to guarantee some kind of overlap between when two users are online or not. Yeah, so that's all that I have for new changes to the protocol document. Are there any questions on this right now before I go into the next section?
Nobody's hopping up to the mic.
Sounds good. So the next section is self-balancing prefix trees. So this is actually something that we've been talking about adding to the draft for a while, and I don't have a PR that corresponds to this exactly. I just was going to present the work that I have and try to get feedback if I can. So the prefix tree is a pretty fundamental building block of the protocol that we're working on, and its purpose is to map search keys to values, and it implements this kind of like map data structure abstraction. And the way that it's actually implemented in the document is with a data structure called a trie. And with a trie, you have a root node, which represents an empty prefix, and then the left subtree of the root node contains every search key that starts with 0, and then the right subtree of the root node contains every search key that starts with 1. And then you kind of recurse like that, just dividing by 0 and 1 until the prefix of whatever search key you're looking for is uniquely defined. And then that's your leaf node where you can stop. And so the motivation for changing this to be self-balancing is the degree to which there's interest in using KT for non-privacy sensitive applications. So if you're using KT for something which is not privacy sensitive, then it would be really wasteful to use a VRF, which is what we pass all of our search keys through right now to preserve their privacy. So the fact that we use a VRF, the transparency log is the only person who has the VRF private key that can actually execute the function, which makes it really hard for people to predict the value of what's going to be inserted into the prefix tree. So people can't kind of like maliciously make some really long path to make some request inefficient. And that's with the VRF. But if you get rid of the VRF, that's not true anymore. And people actually can try to fix a lot of bits of a search path, even if you put it through like a hash function, and make the request very inefficient. And then also just probabilistic balancing that we get from the VRF inserting random values into the tree tends to have a very kind of wide inefficient spread anyways. So this graph that I have here is it's a histogram of leaf depths if I've inserted 2 to the 16 leaves in a prefix tree. So there's kind of this peak around a depth of 17, which is about what you'd expect, but also there's a tail pretty high all the way up to like 30, or you can pretty easily get like more than 30, where this leaf is 30 levels deep in the prefix tree, even though there's only like 2 to the 16 entries, which is it's a lot. The thought was at the last IETF that we could pretty easily just replace this try implementation with some kind of generic, like, balanced search tree, and that would work great, and we would be done. The problem with that is that typical balanced search trees store data in their intermediate nodes rather than just at the leaves. And so what that means is that if we're providing some kind of like cryptographic search proof for a lookup in this tree structure, with the try, we only have to provide copath hashes for users to verify. If we were going to use the balanced search tree where intermediate nodes have a left and a right child and some data they store, then to provide a search proof with that, we would need to provide the copath hash and also the data that's stored in that specific intermediate node. And what's funny is that would actually make proofs twice as large because you're providing 2 hashes for each step of the search rather than 1, which actually locks in the worst case performance we have with the prefix tree, where with the prefix tree, the average case is 16 or 17, but the worst case is 32 hashes that we have to provide. If we were to do a balanced search tree, then maybe the search step is always exactly 16, but we have to provide 2 hashes for each of those 16 steps, so 32 hashes total. So that's actually the worst case. So the solution that we kind of worked out, the solution that I've kind of been working on for this, to provide some framing for that, I wanted to first talk about how searches in the prefix tree work right now. So step 1 of a search, you have some kind of range where 0 is on the far side and then 2 to the n is on the other side. And what you do is you take your cursor and you just put your cursor right in the middle and you ask, is the value I'm looking for to the left or the right of this? And if it's to the left, then you move left. If it's to the right, then you move right. And so in this case, you always just kind of take the open section of the range and you put your cursor in the middle and you keep subdividing like that. And that's how that works. And it is logarithmic, but it's logarithmic in the total size of the range. And the range here is very, very large because we're inserting 32 byte values. So the maximum possible value is 2 to the 256. So the sort of insight here is that search length, or how long it takes for a search to actually complete, depends on the density of data that's stored in the tree, not just like the total range of possible values that can be inserted. So if we could actually like see the density of data that's inserted, like in this case, we can see that most of the data is sort of all centralized in the right half of the tree. Then we would actually know that this first lookup with the cursor is kind of wasted time because it's not actually excluding very much data. If everything is already on the right, you're always going to move to the right. So there's no point in doing that request. So the way that we kind of handle this is that we allow multiple starting points within some range that we're trying to search through. And at each step in the as we're conducting the search, the transparency log can tell the user which place is going to be most efficient to start the cursor, or at which place in the range is going to be the most efficient to place the cursor. So in this case, we have 3 options for where to put the cursor, A, B, and C. C obviously divides the data that we have the best and have, so that's going to be the most efficient place to place the cursor because you're going to have immediately 50% of the data on one side, 50% on the other. And so if you kind of take this idea and do some empirical tests with it, which I did, the cases that I tested is this number of cursors column here. The first row is we always just have 1 cursor, so that's the typical unbalanced prefix tree. Then under that, we allow 3 possible cursors that the transparency log can choose from, and then 15, and then 255. With each of these search trees, I calculated the average leaf depth. So for some leaf, how deep would you expect it to be in the prefix tree? When the tree is completely unbalanced and you insert 2 to the 16 leaves, on average, you'd expect a leaf to be 17 levels deep. if you give the transparency log 3 different cursors that it can possibly choose from, then the leaf depth goes down to 16.8 and then 16.4 and 16.2. And then you can also look at what's the expected deepest leaf. So if you insert through the 16 leaves, which or how deep would you expect the deepest leaf to possibly be? When it's completely unbalanced, you'd expect it to be about twice the average length. So in this case, 34 levels deep. And then as you increase the number of cursor options you have, it goes up pretty quickly. And then you can also compute the overhead, which is essentially how much bandwidth do we have to spend for the transparency log to communicate to the user which cursors it should choose for each search step. So when the tree is unbalanced, you don't have to communicate anything, so 0 bytes. When you have 3 cursor options for each search step, then you have to encode 2 bits to choose between those cursors for each of 16.8 search steps. So that turns out to be 4 bytes and so on. Felix?
Yeah, I don't understand this table because I understood cursors to be an optimized search, not a way to organize the tree. So the leaf depth doesn't depend on the way I iterate a tree, no? So what am I understanding wrong?
Okay, so I think that you are right that it doesn't change the structure of the tree really, but it changes how people navigate the tree. So if I know most of the data is in like one particular side, then I'll move straight to that side.
So what does average leaf depth then mean?
So average leaf depth is how many search steps it takes on average to get to a leaf. So after how many search steps does the search terminate?
Okay, yeah, thanks.
Mhm. And so the reason this is actually kind of really impressive is because the overhead is in all cases much, much smaller than the amount of data that we're getting back. So even in the most generous case, which is we have 255 cursors for each search step, we only have to communicate 16 bytes from the transparency log to the user to make that search work. But we actually take one entire hash output, or we reduce the number of search steps by 1, which means we need to send 1 less hash, which is already 32 bytes. So we've netted 16 bytes just on the average case. But most of the value really comes from the edge cases where leaves are sort of unusually deep in the tree. So in an unbalanced case, the deepest leaf would be 34 levels deep, and the most balanced case, it would be 19 levels deep. So that is 15 hashes that don't have to be sent anymore in exchange for 16 bytes. So, and then another way to think about this is if you just think about the worst case leaf depth, which is if an adversary could fix every bit of the search key that we're inserting, what's the worst possible like search depth they can create for someone? So when it's unbalanced, you can fix every bit and make it 256 levels deep. If you can balance it a little bit, you can only make it 192 levels deep, and so on to 64. Applying this more to like a practical case, if you think about like passing whatever the user inputs into a hash function first, and then inserting the hash output into the prefix tree, this sort of on ratio still applies. So if a user can fix 100 bits of hash function output, then they actually only get 25 extra search steps in the most extreme case. So yeah. And then I also sort of graphed the general search length that you would expect for each tree of different degrees of being balanced. So in the most balanced case, there's a very, very tight curve around this average case of 16. And then in the unbalanced case, you have a much flatter sort of blue curve that corresponds to just an unbalanced prefix tree. And yeah, that's all I have.
Can I jump in there? Yeah. I didn't quite understand the connection of your presentation regarding multiple curses to the original motivation of balancing trees that are not probabilistically balanced. How, I mean, one example I hear being floated around is you have a prefix tree for domain names, and then the children correspond to sub-labels of the domain name, and then that's basically how you walk the tree down. So how do cursors improve the situation for that?
Well, so if you have this idea of like a prefix tree where people insert a domain into the prefix tree, then the search depth depends on, what other domains are also in the search tree. Where if you have like google.com and then you have like googlef.com or whatever, then whatever search path has to go all the way through like GOOGL until you get to like E and F and that bit that's flipped at the end. Does that make sense? Whereas with this case, you
Yeah.
could balance it out. And even the fact that these two values that were both inserted into the prefix tree are very close, that doesn't necessarily correspond to a very long search path.
Oh yeah. Okay. A second connected thought. So having started, you'll hear more about this later. Having started a client reference implementation for key transparency, I find the draft quite hard to implement. Well, this is now, it could be that I'm just incompetent, but I think it is quite a complex beast already. And there is an alternative way to balance prefix trees that do not have privacy requirements. Namely, you just hash them and the labels and don't use a VRF. And then then I would expect you get similar probabilistic guarantees for balancing the tree. And
I
that
don't think
seems to
that
me much simpler to implement and also to reason about when it comes to security. And extends the current draft in a straightforward way. What do you think about that?
Well, so if you just hash what you're inserting into the prefix tree, you can still pretty easily fix a large number of the hash function's output bits, just through brute force, if anything.
To create cases where verification is very expensive?
Exactly, yeah.
Okay, yeah. I mean, the expensiveness of the label does not only depend on the label's place in the tree, but also how often the label is queried, right?
No, we don't. It's not based on how the label is queried, like how frequently it's queried. It's not balanced out like that.
No, but like you only need to create a proof when it's queried. That's what I'm saying. So if you have a label that, like, if you adversarially choose a label that's expensive to query, you'll only generate the actual cost when people query it, and the server needs to provide proof for the inclusion or non-inclusion or whatever, right?
I'm not sure I follow because I think the model that I'm thinking about here is you have like google.com has something stored in a transparency log. And then someone else malicious comes along and can make google.com search path really, really long. Right? So it's someone else.
Because
It's someone else
they have a
coming
long overlapping bit prefix.
with someone else, exactly.
Okay. Yeah, okay. I'll think a bit more about it. Thank you.
Yeah, thank you. Ivo?
Yes, I think I'm next. So I have like one question is, so you mentioned for like the motivation for this second part and like having self-balancing prefix tree is like new use cases. Do you have a list of these use cases? And maybe more like of a process question is like the current charter specifies that KEYTRANS focuses on end-to-end encrypted messaging systems. If these new use cases like would not require privacy are not part of that, is there like some requirement for like rechartering to include that?
I don't have a list of the use cases, But also, I'm not sure if the charter requires us to specifically focus on messaging use cases, which is kind of why I did also give motivation here, which is that, there's interest in using KT for non-privacy sensitive things, but also just probabilistic balancing tends to be kind of inefficient because you have this really wide spread of possible path links that result in you needing to send a lot of unnecessary hashes. So, I mean, even just for strictly for a KT use case, it's still valuable. Potentially, I don't know.
Yeah, no, I mean, I agree. I think it's more that I do think the restriction to like the private use case like has allowed for like some like simplification and like advancement in the protocol. And as we are now considering some more like public use cases, this seems to like make reconsider how like the protocol will work. And I think having like the list of use cases and what we're actually tackling would help like skim that down.
Mm-hmm. Yeah, totally. Okay, any other questions or comments?
All right, I'm taking slide control back. Who's doing this? Do you want a clicker?
Yeah. Do you want to give an intro or do I just jump into it?
Do it.
Okay. So we have two parts, one from me, one from Jonathan. We'll go through them now. This is the outline. I'll start with formal verification. So we have been working on the formal verification of the draft, and recently Corey Myers and Linard R. Quinn joined the team. I especially want, Corey should be in the joining us remotely right now. I especially want to highlight Linard. He's a doctoral student in program verification, and he contributed the skills and insights that helped us actually start tackling the thing on a technical level. So what are the goals of the formal verification beyond the obvious? I mean, what's our current, our current roadmap? We try to reference, we try to verify a reference implementation that we implemented in Golang. We want to verify the client of the reference implementation. For the beginning, any server behavior is completely out of scope. And that is the case because for a client that it's worried about its security and key bindings, the server is the adversary. So the server will not run the code anyways that you think it might run. So we don't verify it because the adversary won't use it. The high-level intuition of the security goals that we try to prove is we want to prove that all clients agree on their view of the log. Critically, this must be independent of any server input they consume because the server is the adversary. So what does agree mean here? Intuitively, we formalize this as they see the same results to the same queries. And on the next slide, I'll go into what that even more formally means. So let's use the latest key query as an example. This is what we are currently focusing also in our verification. For the latest key query, what do clients do? They submit a search request and they receive a search response. Importantly, the response contains the full tree head. And in my reference implementation, this is currently the type signature of this function. It's a bit abstracted just as a footnote, but these details don't matter, which is why I abstracted them. So you have this function verify latest, which takes a search request from the user and a search response from the server, and it outputs an optional update value. It's a pointer just so that we can return null in case verification fails, and an error should an error occur. We start with the following property. It looks quite big, but bear with me. I have shown a similar property in the interim meeting where it was a bit simplified for an imaginary transparency scheme. Now it's our actual one. So the property has three parts. You see a for all a universal quantifier with a couple of variables. Then you see a couple of preconditions on the variables, and then you see the right-hand side of an implication. And this right-hand side of the implication is what I would like to focus you on. So what we want to say is that for all queries that are the same, and Q here is a query, independent what the server response is, R1, R2, we want that these queries return the same result. Now we need to make a couple of side conditions, and they are in the left-hand side of the implication. So what do we assume here? Well, we only want to prove this if the two errors that the E1 and E2, that these two functions return are nil. So there is no error. Verification succeeded. Because it's trivial for an adversary to make a client fail verification. For example, they just give them no proof at all. Then we want that R1 and R2 are operating on the same full tree head. Now, this is not necessarily desirable. This is an abstraction to make proofs easier for now and to test our methodology and to get progress. Eventually, we would like to show similar properties where the full tree heads used in the responses are not the same but related. So one is, for example, a later version of the tree used in the other. And then V1 and E2 are the return values of verify latest. So yeah, and then we get the implication. The results of the verify latest functions should be the same, independent of what the server proof looks like. Eventually, as I just said, we want to reference multiple tree heads. So this property that you see here is a hyper property, as it's technically called. Linar told me that, though in hindsight it was obvious. Why is that a hyper property? Because it relates multiple runs of the program to each other, right? We're talking about two executions of the same function, and we want to say they are related in some way. In general, these are harder to prove, as you could imagine, than non-hyper properties, and non-hyper properties only talk about one execution. For example, I give you a simple non-hyper property about an imaginary sum function. You could say whenever you sum up all values up to n, then this sum function holds. Yeah, this is a not hyper property. You can just walk down the function and check what happens. So now we started on case studies to check our proof methodology. The first case study we checked was for a simple commitment scheme. And commitment scheme really means you get a hash and then later you get the opening of a hash, which is the simplest of the transparency systems. And I can fortunately report the proof methodology worked for that. And there it was trivial. But I mean, you could have failed already there. Then we worked on a simple prefix tree proof, which is not enough, but something. And on a simplified proof, all a bit simplified, but like approaching the actual thing. And it worked there too. And now we're working on an actual client, which is, yeah, so the work that we're doing now is not the ultimate goal, I would say, of the verification we'd like to do, but I think it's still not easy, and it's a necessary first step to get to the ultimate goal. Let's see how far we get. I like to follow the agile road. As part of that, I started to open a couple of issues and pull requests to make the specification less ambiguous and more straightforward. So now comes a bit of anecdotal. Yeah, thank you. So I think the specification does a great job at teaching people key transparency. It's the best written piece on key transparency that I have written, I must say. I find other pieces very hard to understand. I found this easy to understand, but I still found it quite hard to implement. And that is because it, on a couple of places, to me, relies on what I personally find non-obvious insights into how algorithms work and certain corollaries on graph theory. I opened a couple of pull requests to make it less ambiguous, more algorithmic keys, where I say, like 9 steps and here an if branch, and if this, then you return that value, which more closely matches my reference implementation and understanding of the standard. This has a downside that the document becomes less introductory to key transparency. I'm not sure what the right way is. Maybe we can also find something in the middle. I'd be curious about more input there, especially on the issues and pull requests that are open, because it's much easier to discuss this when you have concrete phrasing in front of you and not like just a high level idea. But input there would be great. Maybe questions on the formal analysis before we proceed? Or should we finish first? I think questions now. Finish first? Okay. Come, Jonathan. Now.
There are no questions.
Okay, yeah. Okay.
And
And
now
now.
all go at once.
Yeah.
Okay. Which way is forward?
Try it.
Okay,
There you go.
so this is our first impressions. So obviously we don't have any formal results yet, but things that which I think might cause problems in our work, but roughly speaking, suggestions for maybe improving the draft. So the first one is the signatures in the tree head TBS that you can see at the bottom don't include a domain separator. So they don't have, e.g., the string auditor in them. And if you look at things like witnesses that have been proposed, they also sign the tree head TBS, and therefore you could potentially get confused about who's who, what's what. And so I think just having a domain separator in there would be really, really helpful. And signatures should cover, ideally, the old root hash and config, i.e. you want to say, this specifically is the change that we are signing. We're signing the step from this root hash to that root hash. And this is especially in the third-party auditing mode. Next slide. There we go. And then extensibility. I mentioned witnesses a few moments ago. If we want to have support for things like witnesses, which are, say, partial or weak auditors, then we need a way to make sure that clients agree on exactly what's happening. We need to have some way to make sure that the clients say, I think there are these auditors and these witnesses, and you don't have another client saying, I think there's only auditors and I've never heard of witnesses. So to do this, we need a hook or a place where we can insert arbitrary configuration information that ensures all clients use the same config and have the same understanding of that config, obviously. And so for witnesses, this would include like a commitment to things like key ID, key, role, blah, blah, blah. And so a suggestion would be an extension field in the config, so which gets signed into the treehead TBS. And I think, yeah, that's the end. Thoughts, comments, questions on either part? Fabulous.
You have a question? Yeah.
Hi, Brendan.
I have a question. I have a comment more so. I just wanted to say that working through the issues that Felix has opened related to working on formal verification has been incredibly helpful, both in helping make the language of the draft more precise and also identifying actual like bugs and what I've described. So thank you for all of your work.
Amazing.
That's it.
Well done, Felix.
Okay. Anybody have anything else they want to talk about? All right. Well, thank you very much. Great notes, by the way.
While people maybe still hang around, I heard rumors that people are implementing the draft. Having started to implement it myself, I started like, sometimes I thought I can only do this by the help of a Brandon Oracle. I'm curious about people who implement it and about their experience. So if you implement it, reach out to me, please.
All right. Thank you very much.